In order to compare the characteristics of different PV modules, it is extremely important to test the modules at the same conditions, and that's why all the industries use the standard test conditions. This video deals with the main issues of replicating the solar spectrum with a solar simulator, ensuring a relatively independent comparison and output evaluation of different solar modules. We will analyze the spectral match, the uniformity, and the temporal instability. The standard spectral irradiance of natural sunlight is defined by means of the AM1.5 global spectrum, which is measured on the Earth's crust after that sunlight travels through the atmosphere. The absorption of different molecules yields to these dips, and as you may notice, the spectral irradiance is not evenly distributed, but most of it is located in the visible part where 55% of the incoming irradiance is condensed. In order to replicate the AM1.5G spectrum, a solar simulator is employed. There exist three types of solar simulator: short pulse, long pulse, and steady state. Although the techniques are very different, they must comply to the same standards. So let's start with the short pulse, also called the flash simulator, which is qualitatively similar to flash photography with typical durations of several milliseconds, and it can reach very high intensities of up to several thousand suns. This type of equipment is often used to prevent unnecessary heat buildup in the device during the test. However, due to the rapid heating and cooling of the lamp, which is turned on and off continuously, the intensity and the light spectrum are inherently transient, making repeated reliable testing more technically challenging. The second type of solar simulator is the long pulse, which uses a shutter to quickly block or unblock the light from a continuous source. This category is a compromise between the short pulse and the steady state, having the disadvantage of the high power usage and relatively low intensities of the continuous simulators, but advantage of a stable output intensity and spectrum. Both the long and short pulse are used to measure the performance of the modules because are very quick and can be easily implemented inside the production line. Lately, the steady-state solar simulator has gained attention as it can accomplish different tasks. Eternal Sun is a Dutch company specialized in solar testing technology. Here you can see their steady-state solar simulator at work. Two technicians lay down the PV module on the cart. Then they connect the power output to their hardware as well as the thermocouple in order to measure the temperature of the module at the backside. Next, the cart is moved underneath the solar simulator, the current voltage characteristic is measured, and the power voltage curve is retrieved. Providing with the geometric information of the module under test, the output power of the module is finally known. This type of solar simulator can accomplish different tasks because its illumination is continuous in time. Unlike the previously explained technologies, the latter can also be used for power stabilization measurements, degradation measurements, and light soaking, which is very important because light exposure can produce a variety of effects that influence the determination of both initial and long-term stabilized device performance. The goal of a solar simulator is to replicate the natural sunlight spectrum as accurately as possible. For this reason, the European International Standard uses three performance parameters, and each can score A, B, or C. The first one deals with the spectral match between the light source and the AM1.5G. Of course, the higher is the score, the narrower is the error margin allowed, and in the following slide we will define in more details each category with some examples. Then, the simulator is investigated according to the irradiation distribution on the module surface, and finally, according to the temporal stability of the measurements. Let's start with an example of the evaluation of the spectral match. The EIC standard defines 6 spectral ranges, each 100 nanometers wide, going from 400 to 1100 nanometers. Each range is characterized by a specific spectral match value, and thus the class is assigned to each range. Then the spectral class depends on the lowest scoring category. For example, if you have 5 intervals with an A score and 1 interval with a C, then you have a spectral class C. In this example, all the intervals have class A, and thus the spectral class is A. In order to achieve a close spectral match to the reference spectrum, advanced solar simulators commonly use multiple light sources, and this is generally done by filtering and merging the output of the 2 types of sources, usually an arc source for the visible, like xenon, and a quartz tungsten halogen lamp source for the near and long-wave infrared ranges. Let's move to the second requirement, uniformity. In order to quantify the spatial non-uniformity of a solar simulator, we must map the irradiance of the solar beam over the test area, as the one depicted in blue, where the PV module is placed. This parameter is very important because natural sunlight irradiates extremely evenly over a certain area, and therefore the simulated sunlight should do the same. By dividing the test area into a grid of measurement positions, we can apply the following equation from the EIC standard to easily calculate the non-uniformity in percentage terms. The number of measurement positions to use depends on the size of the test area, but in general the total area is divided into at least 64 equally sized test positions or blocks. In this example, we have 8 times 8 blocks. The goal of this test is to ensure that all the blocks in the test area receive the same amount of irradiance and thus find out the uniformity value that classifies the solar simulator. So, in this example, the irradiance was measured in each of the 64 blocks. Then, minimum and maximum intensities, highlighted respectively in black and white in the figure, are used to calculate the uniformity percentage, also called the intensity deviation. Here, the intensity deviation is 1.29%, which is lower than the 2% value. Therefore, the simulator can score an A, which is the maximum achievable for this standard. The third and the last category to determine is the temporal stability. The general method is to measure the irradiance of the simulator beam over a specific time period. According to this time interval, we talk about long-term stability, or LTI, when we consider the entire time period of the interest. Or we can talk about short-term instability, when we consider the instabilities between the measurement points of irradiance, current, and voltage, or, in other words, when we consider the data sampling time of a dataset. The irradiance measurements are carried out in the simulator via a current voltage measurement system, which consists of a suitable test cell connected to a source meter unit. The short circuit current of the cell is measured repeatedly over the required time period, as shown in the graph, where the typical irradiance of the steady-state simulator is plotted as function of time, highlighting its fluctuations. By using the maximum and minimum irradiance measured, it is possible to obtain the temporal instability, also called the irradiance deviation. In this example, the solar simulator scored an A because the instability is lower than 2%. To recap, in this video we have seen the 3 main parameters to define a solar simulator: spectral match, uniformity, and temporal instability. In the example shown here, the solar simulator scored a triple A.